email me, and that can definitely be taken into account. I have to be careful because the complex analysis class has a midterm as well, and actually my student who sits right over there is a big Tigers fan. And so, yeah, so I might have to do something after last night.
He's done.
He's done. Okay. So what I wanted to do today is start off with a little bit of math on convolutions, and then this is basically putting material in the bank. The two worst times I think to give lectures are right before a major holiday and when students have an exam. The mindset is not always focused on what's going on. So what I thought I would do today is some interesting problems as well as just putting some material in the bank for later. And so what we're going to start off with is convolutions. So how many of you remember the dice problem where we were rolling the die and trying to figure out what's the probability that the sum of the roll is a 1, 2, 3, 4, 5, etc. It wasn't too bad to do, but how many people would look forward to doing it for 3 rolls, or for 4 rolls, or for 5 rolls? So the whole point is we want a better way of attacking these problems. And so convolutions, it's one of our other techniques for attacking random variables. And so it's defined as follows. Fg are nice functions. The convolution is denoted f star g, and its definition is f star g of x is the integral from minus infinity to infinity of f of t, g of x minus t, dt. Okay, so what's the first thought you should have now that this is written down? First thought. Yes?
Is it useful?
Is it useful? Okay. I feel like Family Feud. I think one answer beats useful.
What's a nice function?
Ooh. I think number one answer is related to that.
Is it solvable?
Give me a shorter word than solvable. A better way of phrasing it. What do you mean by solvable?
Integrable?
Okay, so that's, can I find it in closed
Not
form?
shorter.
So is there a closed form? But I think there's one question we should be asking before we get to all of this.
Work.
Does it exist?
Yes.
Does it exist? And I think this is related to what is nice. For what choices of f and g will this integral make sense? And so, as we're in a probability class, what do you think f and g will typically be?
Positive densities.
Positive densities. And so if f and g are positive densities, the question is, will it exist for them? So special case, f and g are densities. So this means that f of x and g of x are greater than or equal to 0, and they integrate to 1. Alright, so we don't have to worry about a lot of things now because our functions are integrable. So clearly, f star g of x is going to be non-negative. So f star g of x is greater than or equal to 0. Why is it greater than or equal to 0? So why must it be greater than or equal to 0? Well, we don't know it's a probability yet. It is a probability, and that would be an answer.
Because if you multiply two positive...
Or two non-negative.
Two non-negative...
Right.
Quantities, and they have to be non-negative.
Excellent. I'm multiplying two non-negatives, so it can't be negative, and then I'm just integrating it. So the only danger is, could it be plus infinity? So now, let's consider the integral from minus infinity to infinity of f star g of x dx. So you had just guessed, was it Chris who guessed? That it was a probability? So if it's a probability, it's non-negative, what should this integrate to? 1. So let's see if it integrates to 1. So we integrate from minus infinity to infinity. Now f star g, I'm going to actually write x over here and t over here just so I remember what my bounds of integration are, what my variable is. So I'll have f of t, g of x minus t, dt, dx. And I'll put brackets to remind myself which way to do things. We have two ways to evaluate integrals. If they're multidimensional integrals and they look hard. We can change variables, or we can switch the order of integration. Which do you think would be useful here? Changing variables or switching the order?
Switching the order because the f of t becomes constant.
Good, the f of t becomes constant if we switch the order and integrate with respect to x first. So we need to be able to justify switching the order. Well, we can use Fubini's theorem as everything is non-negative. So switch by Fubini, all is greater than or equal to 0, so all is okay. And we get the integral t goes from minus infinity to infinity, the integral x goes from minus infinity to infinity. I can pull the f of t outside, and I have g of x minus t dx dt. What's the integral of g of x minus t as x ranges over everything? So what would that integral equal?
Just g of t.
Not g of t. Why 1?
Because
G is a probability density. I could change variables. If I let u equal x minus t, du is dx. So my change of variables is going to depend on the point t. But really, as x ranges from minus infinity to infinity, it's the same as the argument of g ranges from minus infinity to infinity. So we get the integral t goes from minus infinity to infinity, f of t, and then we have the integral, now it's u goes from minus infinity to infinity, g of u du dt. And the integral of g of u is? That's going to be 1. And now what's the integral of f of t dt? 1, because it's probability densities. And so this proves that it does integrate to 1. So we've just shown f star g is a probability density. Okay? So that's a nice fact to know. So we can conclude f star g is a probability density. If you had to guess, what would you guess f star g is the density of? So if it's a density, this should be something which has it as a density. So let's just summarize what we have. So maybe random variable x1 with density f, x2 with density g, f star g of x is the integral from minus infinity to infinity of f of t, g of x minus t dt. What do you think that this is the density of? What would you guess? So I'm fixing a t, and then I'm looking at f of t times g of x minus t. If you try to convert this into probability language, what do you think f of t times g of x minus t would represent?
The probability of an event happening.
Okay, which event? So f is related to which variable?
x1.
So this would be the probability, basically, probability x1 is t, and what would this be?
Probability that x2 is its complement.
Not its complement. Where am I evaluating the probability density? I'm evaluating it at x minus t. So here we evaluated f at t, and we said that this is like the probability that x1 equals t. So what should this be? The probability that x2 is x minus t. Ah! So what random variable does this look like? So if x1 is t and x2 is x minus t, and then we integrate over all possible values for the first random variable, we integrate over all possible t's, this is looking at all the different ways that what could happen. So I need something involving x1 and x2. Looking at this, what kind of relationship do you see between these two things? So I've got x1 is t, x2 is x minus t.
They sum to x.
It looks like they sum to x. And then I'm integrating over all possible. So I'm looking, how could x1 plus x2 equal x? Well, x1 could be t, and x2 could be x minus t. And I have to integrate over all possibilities. This is the probability that x1 plus x2 equals little x. Or better yet, it's probability density. So the probability density of x1 plus x2 equaling x is just the integral from minus infinity to infinity f, no, that is x1 of t, f of x2, x minus t, dt. This is going to make it a lot easier to calculate probabilities of events, or probabilities of sums of random variables. Now, whenever you see a symbol like this, you want to ask, why are people using this notation? What does this symbol remind you of? When you see a star like this? It looks like what? Yes?
Multiplication.
It looks like multiplication. So, does this look like multiplication of functions? Yeah, it's not pointwise multiplication, but it is a multiplication of functions. So we use star as it looks like multiplication. Okay? And smiley face was taken for something else. Okay. So it looks like multiplication. So as soon as you have something that looks like multiplication, you should have a couple of thoughts going through your mind. What do you know about multiplication? What kind of properties does multiplication have that you like?
It's commutative.
It's commutative. So I would rather do gambling today than do algebra. So I'm going to just sketch how you would do the long proof of commutativity and then give you the shorter proof. So star is commutative. The proof is just algebra. Show the integral from minus infinity to infinity of f of t, g of x minus t, dt is equal to the integral from minus infinity to infinity of g of t, f of x minus t, dt. What do you think will be useful for showing these equalities? What do you think we'll have to do to get these to be equal? So here I'm evaluating f at t, here I'm evaluating f at x minus t. I need to change variables. Right? So if you do some algebra with changing variables, it should work out. And you can even use this to try to figure out, well, if I want f of t, I want to be integrating with respect to some new variable u. I want f of u, g of x minus u. So this suggests what you should try. What would you try? Try u equals x minus t, and then du would be negative dt. So try that and see if you can get it to work. I'm going to show you a faster proof. Proof by parentheses. Okay? Can someone tell me what x1 plus x2 equals? There are
Two
two.
plus x1.
Yes. Thank you. And he's actually, he might have intended to be a smartass, But it was the
We're doing commutative.
right. No, I know. I said you may have. I didn't say you were. I just said you might have. The smart ass answer would have been x1 plus x2. That would have been useless, right? But x1 plus x2 is x2 plus x1. This is useful. The convolution inherits its commutativity from the commutativity of addition. Why? x1 plus x2, that's what this density is. x2 plus x1, that's what that density is. Does anybody know another nice property multiplication has? It's commutative, distributive, what else? Associative. You can do associative with parentheses as well. Okay. All this stuff works as nicely. Okay. Any questions on convolutions before we get into gambling? Alright. So, first off, I do not advise anybody to go down to Las Vegas or any other places like that and gamble. However, if you are going to do that, at least please listen to the following so that you will minimize your losses. Okay? How many of you have ever seen the game of Roulette? Okay. Can someone describe Roulette for me? Yes.
So there's a certain board where people sort of bet on what a spinning wheel.
Okay.
There's a spinning wheel with numbers from 1 to 36 alternating red and black. A ball is sort of shot down a little thing and then goes spinning around the wheel until it lands in one of those things.
Okay.
People make bets on whether or not it will either be black or red, or they might put money on an individual number.
Or evens.
Or evens or odds.
Or green.
Ah, this
Yes.
green. So in the real world, there's actually two greens.
Yeah, 0 and double 0.
0
Oh.
and double 0. Now, double 0 is not the same as infinity. Okay? What do you think helps? Having greens or not having greens?
Helps you.
Depends on who you're helping.
Yes. So helping you, the gambler,
Not having.
not having them. So typically the way it works is you can bet maybe $1 on red. If red, win $1. Else, lose $1. Well, if this is going to be a fair bet, if you're going to be indifferent about this bet, what should your probability of winning be?
1/2.
1/2. If you have the two greens, your probability is a little bit less than 1/2. This is an advantage for the casino. Well, this is an ideal world. We can rob the casino of its advantage. Do not try to do this in real life, okay? Don't try to cover up those squares. But, for the sake of analysis here, we will assume that there is no 0 or double 0. The analysis I give you will work in the case of 0 and double 0 as well. It'll just take you a little bit longer. Okay? So now we're in this situation. I'm only going to let you bet on red or black. You can bet $1, and if you win, you get $1. If not, you lose. If you bet $5, you win, you get $5. If not, you lose $5. Okay? All right. So the question is, what's the best way to bet? Assuming you do not know the outcome of the wheels. The other thing is, we will assume the different spins of the wheels are independent. This is not necessarily true. For instance, I don't know, the casino might see that there's a lot of money on the table on blacks. And if that's the case, I'm not convinced the spin might be independent. Right? But let's assume all the spins of the wheels are independent. How many of you have heard of the strategy of double plus 1? So I'm going to give you a strategy, fail-proof, guaranteed to make you money at roulette. Normally I would charge people for this, but since this is Williams College, you've already paid tuition, so you get the lecture for free. Right? Guaranteed to work. Okay? So here's how it goes. You bet $1 on red. If it's red, what happens?
Win $1.
You're up $1. If not, down. So now we bet $2 on red. If red, we lost $1, we just won 2, what happens? We lost $1, we just won.
Up 1.
We're up $1. If not, how much are we down?
3.
So how much do we bet? 4. If red, $1. What happens if it's black? How much are we down?
7.
So what do we bet? We're doubling each time.
Oh.
And how much do we win in the end? We are
1.
1 plus 1. Right?
Or really believe it.
Alright.
Really, really love black.
So the process just continues like this.
Yeah.
Now, what's interesting is if you actually go to Vegas or casinos, they've changed from when I was a kid, and you can interpret that any way you want. What they now do is they show you the outcome of the last few spins of the wheel. Airports. If you actually fly through Las Vegas, they have various, games you can play while you're waiting. You can also play, whose flight will come next. But they will tell you what the last few spins of the roulette wheel are. And there are 2 types of morons in the world, and Vegas doesn't really care which type you are. There's the ones who go, oh, red's come up 5 times in a row. Red is hot. Let me bet on red. What's the other type of moron?
Reds come up 5 times. Black
Definitely
must be
gonna
due.
Black must be due, right? They don't care which type of moron you are. As long as you're the kind of moron who will put money on the roulette wheel, if they can get you gambling, odds are they will get your money. So they will announce the previous spins. So all you have to do, this is the lather, rinse, repeat method. Right? You do this and you make $1. Do it again, you make another $1. Now, I love teaching so much and I love grading exams so much that I just would much rather do that than make money. Either that or there might be a subtle flaw here. What is an issue with this? Yes?
It presupposes an unlimited amount of funds for one.
Okay. Do we have any econ majors here? No econ? Okay, one. Okay, 2. So, as econ majors, are you used to unreasonable assumptions? Yes. So, since today's lecture intersects with economics, I will allow myself to make a semi-unreasonable assumption. Also like rodents of unusual size. The rich uncle aunt hypothesis. Now, unfortunately, the rich uncle aunt hypothesis is not quite strong enough to solve the problem. I need a little stronger version. I need the ERUAH.
Extremely.
No, extremely is close though. I need the eccentric. Right? So I posit the existence of an eccentric aunt or uncle who has an unlimited amount of funds, who is willing to bankroll me, but will not give me $1 directly. So if I ask for $1 trillion to place on a spin of a wheel, the eccentric rich uncle or aunt will say, sure, here's $1 trillion, have fun. And if you run out of money, I'll give you more. But they will not give me $1 directly. Right? They think it's very important that I learn how to make money for myself with their extensive bankroll. For those of you who study business, this is actually not so reasonable with some people. Anyway, so I will assume that whenever I need to place a bet, I can place a bet. So the problem of being able to have the emotional fortitude to put down $1 million, I won't worry about that. It's not my money, and I have plenty of it. Okay? There is another problem with this, and to figure out the other problem, you do need to know a little bit about how roulette is actually played. So we had a really nice description of roulette, but something was missing from the description. There's a little bit of an asymmetry here. What we're saying is, if we ever want to place a bet, we have the funds to place the bet. What is that assuming? So I'm going to the table and say, okay, I want to bet $1 trillion that it's going to be red.
The casino has the funds to pay it back.
Not just that the casino has the funds to pay it back, but something a little bit more basic than it has the funds.
The casino wants to pay
Table
it
back.
Well, the casino definitely doesn't want to pay it back.
No. It's willing to be
The casino is willing, yes.
Yeah.
Right. Assuming casino takes bet. Right? What is the probability that the casino takes the bet? Well, the more money you're asking to place down, the less likely it is that the casino is actually going to be willing to accept the bet. So casinos have what's called maximum and minimum table limits. You can have the high stakes table, you can have the low stakes table. How many of you have read either Bringing Down the House or watched the movie? And so in that situation, what they did is they had some people who, this was, counting cards in blackjack. And what they would do is they would have some people who would just be minor people at the table. 21.
Yeah.
Oh, 21, okay.
That's what the movie is.
Yeah, okay, yeah, that's right, the movie's 21. And so they would have some people, their job was to just always bet the same amount, and then as soon as the table became hot and became advantageous, it would look very funny if all of a sudden they started changing their betting profile. So they would signal to people, usually not something, something a little bit more subtle, but they would get people to come to the table. And these people would always be high rollers, they'd always be throwing down money, it would not be out of their profile. What would be out of their profile was always going to lucky tables. So you'd sometimes have to deliberately lose, but they would have ways of alerting people. But each table has a maximum and a minimum bet. So say minimum is $1, maximum is say $20. So a factor of 20 from maximum to minimum. What could go wrong now?
You could run out of your limit. Yeah, you could just get black enough times that
Black, 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 black. So I bet $1, $2, $4, $8, $16. I want to bet $32. But the table won't let me bet $32. They'll only let me bet 20. And so that's the problem. And again, this is of course assuming the eccentric rich aunt or uncle. But even if we have them, we could get into a situation where we might have 5 consecutive blacks and we go bankrupt. Well, no, so we don't go bankrupt, but we can no longer place the bet we need. So the problem is when you win, how much do you win?
$1.
And how much do you lose?
16.
Oh, more than 16.
Or,
One less than 32,
oh, okay.
right?
Yeah.
You have to lose $31 because you're summing 1 to 16, so the faster, yes.
you could keep moving up to the hot next stakes table.
Okay, so yes.
Keep going.
I'll produce you.
So how many of you have heard of the Hilbert Hotel? Did we talk about that?
Yeah.
Yeah, so if you're playing this game in the Hilbert Hotel, and if there's a casino in the Hilbert Hotel, then yes, this would work. If you think it took a while to build the library here, just wait until you see how long it takes to build the Hilbert Hotel. Okay. So what I want to do now is I want to do a clicker question. We haven't done a clicker question in a while. Alright, so this is a simplified roulette game. What a surprise, it relates to what we just did. Where red occurs 50% of the time, black occurs 50% of the time, and the spins are independent. What is the probability of getting at least 5 consecutive blacks when the wheel is spun 100 times? Alright, so everybody, spinning the wheel 100 times, and I want to know what's the probability I get at least 5 consecutive blacks. So the answers are less than 1%, about 5%, about 20%, about 50%, 80%, 95%, or more than 99%. Alright, I will open it up for voting. The polls are open. We need 16 votes today. We're at 9, 10, 11, 12, 13, 14, 15, 16. Just making sure it doesn't go above 16. Okay. Alright, so the answers, let's see. So I will record these answers for later. We got B had 6%, and B was how many? 5%. I'll do it like this. C had 31%. And how much was C? 20. E had 31%. How much was E?
80.
F had 31%. That was 95. Okay, and nothing else. Good. Okay. In the interest of time, I'm not going to do the second question, but it's very much related to the first. Instead, I'm asking about how many spins do I need to have a 50% chance of observing at least 5 consecutive blacks. So I'll let you think about that. So you can use Mathematica to solve recurrence relations. The first time I tried to use Mathematica at Williams, I was teaching differential equations. And I was showing my students how to use Mathematica to solve recurrence equations, and it didn't work. And then I realized, oh, the version I have on my laptop is one later than the version on the Williams server. And so they had just added recurrence relations. So hopefully you've seen the Fibonacci recurrence. So the Fibonacci's is fn plus 2 is fn plus 1 plus fn. So you write it as fn plus 2 minus fn plus 1 minus fn equals 0. Use the double equal sign to just mean zeros. You then feed in the initial conditions. F of 0 is 0, f of 1 is 1. You tell it to solve for f of n. The index variable is n. You plug this in. Oh, there's a typo. The letter R seems to have been cut off. I'm not sure. It might still work with the word solve instead of R solve. What do you think R solve stands for?
Recursive.
Recursive solve. So I can't remember if it will work with solve as well. We will show in a little bit later today that you can actually use Mathematica to find the solution to the double plus 1 problem. When you use Mathematica, there's sometimes some issues. It will actually try to keep things exact as long as possible. So it will find answers in terms of the roots of a polynomial of degree 5. So in order to override Mathematica, what you do is you just put in 0.0. When you put in one real number, that forces it to get an exact answer. If you look at this, you should see something that looks a little strange. You have to have really good vision. And everybody see it? Yes?
It's an I at the end?
Yeah, that's the square root of minus 1. The square root of minus 1 actually occurs in the solution. Now it turns out everything cancels. And all the imaginary stuff cancels, and in the end you're left with a real number. Now Mathematica, since it's doing floating point operations, sometimes it's off by a little bit. It will have an imaginary part in the answer of around 10 to the negative 17. So you can override that by just forcing it to take the real part. And so you can get a nice function, and you can just plot it. Alright, so what I want to do is I want to show you how you can solve problems like this by using recurrence relations. Later in the semester, we're going to talk about generating functions. Generating functions is one of the most magical things I know of in probability, where it allows you to take some information and generate incredible explicit formulas for it. So, recurrence relations. So the goal here is to introduce some of the basics. We're going to be putting some knowledge in the bank for later in the semester. I don't know if we're going to have time to actually get to the generating function solution to the recurrence relation of the Fibonacci's today, but we will at least be able to see that the double plus 1 game is actually a recurrence problem. So, Fibonacci's. Fn plus 2 is Fn plus 1 plus Fn. F0 equals 0. F1 equals 1. The sequence is 0, 1, 1, 2, 3, 5, 8, 13. You've all seen that sequence at least once in this class. This is the password to anonymously email me. Right? So if you forget the password, just start generating the Fibonacci numbers. And I think it's the first 8. How many of you have seen the Fibonacci's before? Okay. What I want to do now is I want to show you that the same math that's used to solve the Fibonacci's actually solves the recurrence relation, a recurrence relation associated to double plus 1. If I give you 2 Fibonacci numbers, can you find the next one? And the next one? I'm sorry? If they're consecutive. In fact, even if they're not consecutive, you can still find the next one. It's just more work. If I give you the 100th and 101st Fibonacci number, you can find the 102nd. But at some point, this stops being fun. You know, for me, it stopped being fun around 13. Right? You might be able to go a little bit further before it starts getting a little bit painful. But there is a solution. It walks things out. It's also very expensive. If you want to just jump to what's the 200th Fibonacci number, you don't want to have to compute everything beforehand. You want to find a way to just jump to the 200th. There's a beautiful formula called Benet's formula. How many of you have heard of Benet's formula? Okay. Can somebody tell me a property the Fibonacci's have? What kind of numbers are they?
Integers.
Integers. This is an explicit formula for the nth Fibonacci number. I think I might have mentioned it in the class. If you see a police lineup and you have to identify the integer, this should not look like an integer. it has division by 2, it has radical 5s. This turns out to be an integer. What's so great about Benet's formula is it allows you to jump immediately to the nth Fibonacci number without pre-computing all the previous. This is a dangerous question to ask now, so I will not ask it. I will just say, if you happen to remember linear algebra, and if you happen, I hope this is not subjunctive, and you happen to remember diagonalizing matrices, you can solve the Fibonacci numbers through diagonalizing matrices. And you can create an eigenvalue eigenvector problem. You can write your vector in terms of a linear combination of the eigenvectors of an associated matrix and jump to the nth Fibonacci number. It's another way to get this. We do have methods to solve recurrence relations. The method we're going to use primarily in this class is either the method of divine inspiration or generating functions. So the way divine inspiration works is you write down the answer and you say, here's the answer. And so what you can do is check. When n equals 0, we get 1 over root 5 minus 1 over root 5 is 0. Good. When n equals 1, after the root, yes. And you can prove by induction that this works. So the method of divine inspiration is a very powerful way to solve problems. It's also a little bit spotty in terms of its track record, and you're not always sure when you will be divinely inspired. So it's nice to have a fallback approach. Generating functions will be our fallback approach. So let's return to double plus 1. So I'm going to let an be the probability we have 5 consecutive blacks in n spins. What do you think Bn is going to be? So A is the probability we do have 5 consecutive blacks in n spins. What's another thing we could study? That we don't. 1 minus an, probability don't have 5 consecutive blacks in n spins. So everything I'm doing now is actually available on a 6 or 7 minute YouTube video I did with OIT a few years ago. So if you want to just sit back and enjoy the gambling, by all means feel free to do so. Alright, which do you think is going to be easier to calculate, AN or BN?
BN?
BN. BN is the easier one to calculate. If you were having trouble calculating BN, what should you do? If this turns out to be hard, what would you try to do instead? AN. Now you have a 50-50 chance. Start trying to calculate one of them. And if it becomes hard, shift to the related one. If I understand BN, I can understand AN very easily, and vice versa. Alright, so I'm going to start off here. And I'm going to try to calculate the probability I don't have 5 consecutive blacks in n spins. What are the possible outcomes on the first spin? What could happen on my first spin? Red or black. If I wasn't lecturing in here in the next hour, I might actually use, crayons or chalk that's multicolored, but then I'd be screwing myself. So I could have red and I could have black. What's the probability of each event happening? A half. So the question I'm about to ask, once you answer this, the entire problem is done. It's just a matter of cleanup. Given that my first toss was red, what is the probability that I do not have 5 consecutive blacks in n spins? So that's the question. Given that the first toss is red, what's the probability I don't have 5 consecutive blacks in n spins? What would that be? I'm sorry? Not Bn. Why Bn minus 1? Because we've already done one spin. I have n minus 1 spins left. The first spin was not black. So it's really like I'm playing the game with n minus 1 spins. Is this the same as the basketball problem, which I love? Which was a memoryless process. Is it the same as that? When Larry Bird and Magic Johnson both missed, is that the same as I spin and I get a non-black? There's a subtle difference between the two.
No, because If you don't get a black, it alters the probability for the next. That
It doesn't alter the probability. But something has changed.
the number of
The number of spins. It's not the same as the basketball problem. The basketball problem was memoryless. If we said Larry Bird and Magic Johnson were going to shoot, but they were going to stop after 200 spins, then that would be a lot closer to this. So here, the probability is now Bn minus 1. So now I spin again. And every time I do this, I always wonder why I always choose a number as large as 5. Red, black, 1/2, 1/2. What's the probability I don't have 5 consecutive blacks, given that I start black, red? So I don't want 5 consecutive blacks and spins, and I start black, red. Bn minus 2. And then on the YouTube video, we just sped up time at somewhere around here. Right? So that's red, black, 1/2, 1/2, Bn minus 3. Red, black, 1/2, 1/2, Bn minus 4. And I'm running out of board space, this is not good. Red, black, Bn minus 5, 1/2, 1/2. I've run out of board space, really. Is that bad? Do I have to worry about more splits? Why not?
Because you have 5 black.
They're all black here. Black. So what's the probability in n spins I don't have 5 consecutive blacks, given that I start off black, 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 black? Given that I start off with 5 blacks?
0.
0, right? This is one of the nicest problems I could ask you, right? If you start off with 5 consecutive blacks, what's the probability you don't have 5 consecutive blacks? This is why Bn is a little bit easier than An. If it was An, I would actually have a 1 over here. Okay? Any questions? So now we can actually write down the recurrence relation. So we get Bn is 1/2 Bn minus 1 plus 1/4 Bn minus 2 plus 1/8 Bn minus 3 plus 1/16 Bn minus 4 plus 1/32 Bn minus 5. Half the time I'm here, and I have Bn minus 1. A quarter of the time I'm here, I have Bn minus 2. An eighth of the time I'm here, a 16th, a 32nd. Here's my formula. All I need is 5 consecutive values of B, and I can get all the values of B. And I can just march down the line. Can anybody give me a value of B that's easy to compute?
B1 and 0.
Okay.
Or 1. Wait, that we don't have blacks. Yeah,
Right, so if I spin the wheel once, what is the probability I don't have 5 consecutive blacks? 1. Can you give me other numbers where it's easy to calculate Bn? Other values of n?
2.
2. What else?
3.
What else?
4.
4. What else?
That's not that bad.
0. Yes, go back to 0. Right? B0 equals B1 equals B2 equals B3 equals B4 equals 1. And if you plug this in, you can then find the value of B5. The value of B5 would be a 1/2 plus a 4th plus an 8th plus a 16th plus a 32nd, which comes out to 31 32nds, which is what you would get if you just try to calculate directly. The only time I lose is if I have all blacks, which happens 1 out of 32 times. So we can now march down the path. Okay? So later in the semester, we'll see how to solve this by using generating functions to get something like this. There might be time to start sketching that a little bit, I'll see in a moment. So does anybody have a thought of what the answer should be? Oh, guessed earlier. Anybody want to make a strong case for their argument? So here's the plot. So if you look at the plot, probability is very small. So this is the probability of at least 5 consecutive black spins versus the number of spins. So not surprisingly, if I'm spinning at most 4 times, the probability is 0. And then you can see the probability is growing. Are you surprised that the probability never reaches 1? No, we've all read Rosencrantz and Guildenstern are dead. It's possible to keep getting, all reds. It becomes more and more unlikely. So the 50% mark, I figure out, roughly, I don't know, looks like around 40. To give you a sense of how long you have to go before you have a 50% chance. If you're spinning 100 times, I don't know, it probably looks pretty close to 80, I'd say. So for the people who said 80%, well done. You have good intuition. If you know not to go to Vegas, you have even better intuition. So the question becomes, how do you get a nice explicit formula for this? How do you get something like Benet's formula? And so we'll talk a lot about that in terms of using generating functions to solve problems like this. We still have, I think, 2 or 3 minutes left. And so this is not enough time to start talking about how we would use generating functions to get the answer. But it is, I think, enough time to mention an issue in terms of actually doing computations. So I strongly urge you to go to Mathematica and try to put this code in, try to actually get it to solve this recurrence relation and other things. Become familiar with using programs like this. The other thing is to get a sense of what algorithms are being done in the background. So when we're solving stuff like this, what we typically need to do is we need to work with roots of polynomials. And so if I gave you a polynomial, what kind of polynomial would you like to solve?
Linear.
Linear, right? ax plus b equals 0, no problem. We can solve that. What else can we solve? Quadratic. So I give you ax squared plus bx plus c equals 0. You've probably all seen a proof of the quadratic formula, but let me just highlight how you would solve this. What's the easiest quadratic to solve? And I don't consider this a quadratic. I want the a term to be there.
X squared.
X squared. So we can solve x squared equals 0. Tweak it a little bit and make it solvable. We can solve
ax squared.
ax squared equals 0. Tweak it a little bit more. What else could we solve?
Ax squared plus c.
Ax squared plus c equals 0. And so this is where the idea of completing the square comes in. If we have something without a linear term, we can solve it. So when we take this, we want to write this. We'll write it as ax squared plus b over ax plus c equals 0. We want to put something in here to reduce this to a square. So we have ax squared plus b over ax. We need a plus a what? B squared over 4a squared. And then we have to subtract b squared over 4a squared. And now if I just multiply this out, I get ax plus b over 2a squared. And now I'll get plus c minus b squared over 4a equals 0. And so I've reduced the general case of the quadratic to a case of a quadratic with missing linear term, which I can solve easily. It turns out that there's a way to solve cubics. There's an explicit formula for cubic. It doesn't really impress people as much as memorizing digits of pi, but there is a formula for the cubic. There's a formula for the quartic. If you take abstract algebra or Galois theory, you'll learn that there's no explicit formula for the quintic and higher. You can't write down the solution in terms of just the coefficients of the polynomial in general. And you have to resort to numerical approximation. And so that becomes an interesting subject as to how do you actually compute with stuff like this. I can write a recurrence relation for this. I can march down the aisle with a recurrence relation. But if I want to jump, I need a way to approximate with this. Alright, so this is a good place to stop. I will send you an email on what you should be thinking about for Monday. I hope to see you all at the top of the mountain in that gorgeous weather that we're going to have.